Hi everyone, welcome to ME++ with Omkar. In this video, we'll be solving two very easy problems, but nevertheless important concepts in terms of linear algebra and machine learning. We'll just take a matrix vector dot product. We'll take a look at this problem. Actually, I want to open both the problems in couple of tabs. This is one problem, and we'll take a look at transpose of a matrix. So before we go ahead, I'll just show how a basic operation would look like. We can take this example to begin with. In fact, we can take this matrix. I'll show how the transpose would look like and how a dot product would look like, and then we can go ahead. So people who already know, who are already familiar with what a transpose is, what dot products is, they can just jump to the code implementation, which is also going to be like fairly simple, to be honest. Anyways, coming to, so let's just define some matrix. Well, let me define the exact same matrix that they had defined. So let's call some matrix M. So it was 1, 2, 3, 4, 5, 6. So this is a 2 by 3 matrix because we have two rows, 1, 2, and we have three columns. This is a 2 by 3 matrix, right? If I say transpose, M transpose, what this basically will do is, it's like, flipping it on its head. So dimension will become 3 by 2, and the matrix is going to look like 1, 4, 2, 5, and 3, 6. Now, the easiest way of understanding a matrix is if we start assigning the positions. So the original positions in the matrix, 1 is at position 0, 0, 0th row, 0th column, 2 is at 0, 1, 3 is at 0, 2, 0th row, second column. I'm talking in terms of computer science. We start with index 0. Then 4 is at the first row, 0th column, 5 is at first row, first column, 6 is at first row, second column. Right. Now, once you have flipped this 1 still remains at 0, 0, but 4 4 was originally at 1, 0, now it is at 0, 1. 2, which was originally at 0, 1, is now at 1, 0. 5, which originally was at 1, 1, is still at 1, 1. Okay. 3 was originally at 0, 2, now it is at 2, 0. And 6 was originally at 1, 2, now it is at 2, 1. So one thing that has to strike here is diagonal elements, and not exactly diagonal elements, but elements which are present in the same row and same column will basically maintain their position. For example, here 1 and 5, they were at 0, 0, 1, 1 respectively. They still maintain their positions here and here, but rest of them just get flipped. So if it was at ij, it becomes ji. This is one thing to keep in mind for implementation purpose. This is how it looks like. So transpose will lead to swap of dimensions. Sorry, this will be 3 by 2 matrix now. Right, so 2 by 3 matrix transposed is a 3 by 2 matrix, 3 rows and 2 columns. Now, if we talk about a matrix and a vector dot product, again, let's take the same matrix 1, 2, 3, 4, 5, 6. Let's have some vector. So, for dot product to be possible, the number of columns here need to match the number of rows here. Let's take a 3 by 1 vector 0, 6, and 1. This is our vector. Now, dot products are usually very, very essential in terms of machine learning because we use dot products to compute different scores. We use dot product to compute stuff like cosine similarity. So we have some vector A, we have some vector B. Dot product is um, basically a multiplication of both uh, cos. This is just like multiplication of the mod value of both, and this is cos theta. This is actually the core definition of a dot product. Now, it is important in machine learning because when you have two vectors and you are taking their dot product, this can be directly computed. So, for example, if we have some vector a1, a2 up to n dimensional vector, and some vector b1, b2 up to bn, another n dimensional vector, their dot product will basically be a1 into b1. Actually, this is a2 into b2, so on and so forth. This is a summation, right? It is basically summation ai bi, I from 1 to n. This is what a dot product looks like. Now, once you do this dot product, you divide them with their individual modulus, which will be, uh, root of is a1 square plus a2 square up to an square multiplied with square root of b1 square plus b2 square up to bn square, right? That's how we compute the mod. All right. And once we do that, we can actually find a degree of similarity between two vectors. So there is something called retrieval algorithms and hanging algorithms where similarity is important. So the concept of cosine similarity is very important. So their dot product plays a huge role, right? That's how we compute dot product. Multiply the corresponding terms and take their sum, and you divide them with their modulus. Right. Enough said. Enough digression. Coming back to the topic, if you want to compute a matrix and a vector dot product, of course, this is how the mapping will look like. This multiplied with this multiplied with this. So basically each row of the matrix which has 3 columns is multiplied with the corresponding element, right? So basically, so for each row, element in each column will be multiplied with corresponding element in each row in the given vector. Similarly, this 4 is multiplied with 0, 5 is with multiplied with 6, this is multiplied with 1. So ultimately, the resulting vector will be something like, so 2 cross 3 cross 1, it will result in a 2 cross 1 vector, which will look like, so 1 into 0 plus 2 into 6 plus 3 into 1 is the first element, 4 into 0 plus 5 into 6 plus 6 into 1 is the second element. This is just for clarity's sake, those who are confused or not sure regarding uh, how dot product multiplication looks like. So this is, again, I just wanted to give a very basic primer regarding how matrix transpose dot products look like, how dimensions work. Dimensions have to match because it is picking a row which will effectively become a record in terms of machine learning, taking the corresponding elements of the column and matching it with the elements of every row. Every row, yes. So that's why the number of columns of the first matrix and rows of the vector need to match, right? And this is just the importance part, the the crucial application part of a dot product in terms of machine learning, which is explained. Now we can quickly jump into the code implementation for this. Let's go to the code. So transpose of a matrix dot product, we can implement dot product first. So we just have a list and a vector. So we can do something like m is length of b. Let's say n is length of a. So first of all, the number of rows in B needs to match the number of columns in A. Let's call it some k. So k is length of A of 0. So A of 0 is basically the number of columns. Right, to pick the first record and how many columns are there. So A of 0 is number of columns. So this number of columns in A really needs to match with the number of rows which is present in B. So if m is not equal to k, then what have they told us to return? Return minus 1. Otherwise, if there is a match, then we can just iterate over it. For I in range, we iterate over all the rows in A. So for every row, we iterate. And for j in range, so m and k must be equal. So in that range, so for every row, you iterate over the corresponding column and you need to do a sum. So we can just define some variable here. So the current sum is 0. In fact, let's define it as current sum. So our current sum plus will be, the given matrix is A, right? So it is A of ith row, jth column multiplied with B's jth row. Right? This is what I am trying to point. So for a particular row, the ith column element is multiplied with the jth ith row element of the given vector. So this you keep on doing, and once you do this, current sum is done. So for a row you have processed, and we can just append it to some vector. We can store it some uh, product vector. In fact, we can define it by default. We can initialize it to 0 for I in range. So what will be the answer? So you have k and m are matching. So we have n cross m, n cross k, and m cross 1. M and k match. So it is n cross 1 is the ultimate product. So of course this has to be n, right? So you do this and then product vector I is red. Return product vector. I think this should be enough. If not, we'll see. Slack time. I hope this screen is visible to viewers. Yeah, I think it passed. So if you go back to the problem description, it should appear solved. Yeah, it's solved. So just a little bit over what we did today. Where like very very simple. This is the number of rows in the vector. This is the number of rows in the matrix. This is the number of columns in the matrix. So number of columns in the matrix must match with the number of rows in the vector. That's the first check, otherwise return -1. That's a dimensionality mismatch. You initialize the final answer vector, then we keep on iterating over every row, and then you do the corresponding element multiplication as I explained in the one note. Right, and we return the vector. So this is the first question. Let's go to the transpose question then. Transpose, okay, so this is there with, yeah, so for transpose we have to use this idea. So ij becomes ji. So here what you have to do is m is the number of rows that we have, n is the number of columns that we have, originally speaking. But what we really need to do is that in the final matrix this should be flipped. So uh, matrix answer, so let's call it m transpose. M transpose is a list of list, which is so number of columns becomes the number of rows, right? So this is 0 for I. Let's declare it like this: 0 for I in range this is nested m for j in range n. Am I correct? Is it the correct initialization? Let me think about it. So inside, so when you have a matrix, initially you have m rows, n columns. You flip it, we have n rows, m columns. So for every j in range n, right, you insert a 0 for I in range m. Correct. So this is the number of columns. This is the number of rows. Once you have m transposed, all you need to do is for I in range n or j in range m and m transpose I j is a of ji. We are sure that a of j exists because the dimension of a is just the opposite, right? Do this and return in transposed. I think we should be good enough. Oh, it's not copied, is it? Let's try to run this. Again, I think viewers might not be able to see. Yeah, it got passed. To double check, yes, it has passed. So this is removing the code somehow. The code went by. Not sure where the code went. Where did the code go? and I see the code. Yeah, let's look at the submissions. Yeah, this is the submission. So basically, I'm just initializing a matrix in opposite dimension, m rows, n columns. Ultimately, will have n rows, m columns. This is the initialization. And then you just iterate over the rows and columns, and ij is populated with original matrices ji. This is the idea. Ij, this is what happens in a transpose. So that's it. This is fairly simple enough concepts covered today in this video. But nevertheless, these are important concepts. I mean, of course, these days everything is packaged into ready to go libraries, which you can just directly import and use in our projects. But nevertheless, the underlying concepts, the underlying techniques, the underlying maths remains very, very important and relevant even today, especially when we work in research or you want to build something new. We really need to know what is going on behind the hood. Can't just treat everything like a black box. So from that school of thought, this is really important. So I hope this was fun for you. You got to learn something. Uh, Consider liking, sharing, and subscribing to my channel if you like my content. See you in the next one. Goodbye.